hydrology. Do you think I need to use this microphone? Okay. My research interest is basically in statistical modeling in hydrology. I joined UKM in 2004, and I did my PhD in 2007, and now I'm a lecturer at UKM. Okay, I will be presenting on regional frequency analysis for Peninsular Malaysia extreme rainfall. Okay, the data comes from 1973 until 2012, which is about 40 years data. Okay, we are also using the station-specific data, the site data, not the satellite data, as what was presented by Prof. Maman earlier. And I'm also going to present about extreme rainfall, which is slightly similar to what Dr. Zalina has presented, but in my case, it will be on regional basis. Okay, because what she has presented is more on the specific site. But for this case, I will be combining sites, okay, data from about 80 stations to form regions, 8 regions, and from there, I will do analysis based on those 8 regions instead of at specific sites. Okay, so background on the regional frequency analysis. Okay, in the planning and design of water resources to prevent or reduce extreme rainfall damage, it is important to first estimate the probability distribution. Okay, we statisticians work a lot with statistical distribution, modeling of probability distribution to the data. Okay, in this case of rainfall in any region, from which the probabilities of exceeding an extreme rainfall values can be predicted. Okay, so basically, when we feed something, the distribution to any data, okay, then we will expect to find the probability of the occurrence of that data, okay, the result from fitting of the distribution. The at-site rainfall frequency analysis is commonly used when a sufficient and long enough data record of the rainfall is available. Okay, however, usually the rainfall data lag is insufficient or problem of no rainfall records. Okay, how do we say we can use that data to represent the, for example, for the stations for which we get the rainfall data, if there's the other site does not have data, okay, for the rainfall, then how can use the available data to actually represent the characteristic of the rainfall at the region. Okay. In this case, at-site analysis may not generate guarantee reliable result and may cause inaccurate and unreliable design rainfall estimates. Okay. So due to this problem, okay, the regional rainfall frequency analysis is preferred instead of at-site rainfall frequency analysis. Okay. And by several past studies, it is shown that it is more reliable and accurate than at-site frequency analysis, although data record lengths may be short and lacking. Okay. Okay. So basically, for the regional frequency analysis, we use the information from the gauge site. Okay. That is the main idea behind the RFA, and the 2 steps are the identification of the homogeneous hydrological subregions and the regional estimation within these subregions. So basically, like what I said, we just group all the stations into several regions, and from there we do the statistical analysis and do the regional estimation based on these subregions. Okay. So the objective of this presentation, okay, the study is to delineate regions for 80 rain gauge stations in Peninsular Malaysia using the cluster analysis. Okay, when we have 80 stations and we are going to break them or group them into subregions. Okay, and then we want to identify. Okay, the second part will be on the identification of the threshold. Okay, for partial duration analysis of rainfall series we are going to select 4 duration in this case. Okay, this is the first one is the 0.25 hours, which is 15 minutes, and 1 hour, 24 hour, and 120 hour, which is 5 days. Okay, rainfall based on adapted hill estimators. And the third one is to determine the best fit frequency distribution for the partial duration series data at every region. And finally, to investigate the trend patterns of extreme frequency and extreme intensity using the parametric linear regression and the non-parametric Mann-Candre test. We have seen just now is the result of the trend test, like what Dr. Zalina presented. So this one is based on the regional estimation of the trend pattern. Okay, so the first part, which is on the delineation of the regions. Okay, for the rain gauge station, I'm going to use the cluster analysis. Okay, which groups the sites based on a distance. Okay, or measure reflecting the similarity amongst a set of attributes of the gauge site. Okay, this is by study done by Rao and Srinivas. So the data from the 80 station for 40 years will be used. Okay, and these are the attributes or the variables that are chosen to describe the regional frequency analysis in the cluster analysis. Okay, and I'm going to apply the Watts method for this case. Okay, so the data from the stations will be grouped according to the longitude, latitude, the mean annual precipitation, the total rainfall grouped into these four categories of months in the year. Okay, the first one will be January, February, the total rainfall for January, February, and March. Second, April, May, and June, July, August, September, and finally October, November, December. And we are using the hierarchical cluster analysis. Okay, using the Watts method. Okay, this method tends to delineate the sub-region approximately equivalent in size, and is thus considered more convenient in the context of regionalization of rainfall data. Okay, by Hosking and Wallace. Okay, so this is the background of the Watts method, which is a hierarchical algorithm. Initially begins with each site serving as a sub-region, and is a hierarchical, so it keeps on adding the site. Finally, it will form, okay, more formula for a sub-region R containing S site, where the flat or the rainfall region is presented by the P attributes that we have just now, the latitude, the longitude, and whatnot. Okay, so you will be grouped, okay, to form the regions. Okay, as this is the result of the cluster analysis. Okay, we group them into 8 regions. Okay, which consists of, like for example, the region 1 consists of 13 stations. Region 1 is located on the north here. Okay, and then we have the region 2, which consists of Penang, okay, and Kedah. Parts of Penang and Kedah. Region 3 is here. Okay, Selangor, Negeri Sembilan, and Melaka. And we have a small region here. Okay, based on the attributes, we group another region here. And region 5 is here, the Kelantan area. Region 6 is Terengganu. Region 7 is here, okay, the Pahang, the central of Pahang. And finally, we have the east coast of Pahang and the Johor as region 8, okay, which consists of 8 stations. Okay, and to ensure that, okay, the regions, the stations are suitably qualified in each region, we did two tests. There is the discordancy and the heterogeneity measure test, okay, to test for their homogeneity. And basically the discordancy measure is used to identify stations which are discordant from the majority station in a given region. Okay, if a site is discordant with other evidently similar site, then there may be a problem with the data for the discordant site. Okay, so with a discordancy measure, okay, which is defined in terms of L moments. Okay, so this is the result of the discordancy measure. Okay, if you notice, we have all the 4 time scales here. For 15 minutes, for 1 hour, for 24 hours, okay, which is the daily rainfall data, and for the 5 days data, 120 hours for each of the region. Okay, and these are the discordancy measures, and this is the critical value we used to actually test whether the sites are discordant within the region or not. Okay, from this we found that only one site, okay, at region 3 which are discordant with the rest of the other site, but we found that the difference is not so much, so we decided that to say that okay, we can accept this as there's no discordant problem in this region. Okay, so based on the analysis, okay, it can be concluded that all regions do not consist of discordant station in them. Okay, another measure, okay, to test whether a proposed region may be accepted as homogeneous or whether two or more homogeneous regions are sufficiently similar that they should be combined into a single region. Okay, we want to test the comparison. Okay, one whether all the sites in the proposed region are homogeneous, and the other one whether we can combine two or more homogeneous region as a single region. So we use the test based on the Hosking and Wallis heterogeneity measure, okay, and compare with the bootstrap Anderson-Darling test and the Derby-Knott-Rank test. Okay, and from literature, this guy concluded that Hosking and Wallis heterogeneity measure is preferable when skewness is low. Okay, skewness we compute it based on the L-moment ratio, which is less than 0.23, and if skewness is larger than 0.23, the bootstrap Anderson-Darling test is preferable. Okay, so this is the result, okay, of the homogeneity. Okay, we have the L-moment statistics, okay, and the result of the test, and okay, based on that we conclude that the analysis showed that the 8 regions are actually homogeneous. Therefore we can accept the 8 region that we came out from the cluster analysis result. Okay, so the next, once we have found out what are the region and what are the stations in the specific region, we are going to start doing the modeling. Okay, but to do the modeling part, we need to do some data extraction. Okay, if it's in the case of block maximum, okay, we can take the block as year. So we just take the extreme of the year to be the extreme data which will be used for the modeling. However, we are going to use the partial duration series or Pickover threshold method to extract the extreme data series for each region and at each time scale. Okay, the PDS require the extraction of k independent events from a record length of t years, all exceeding a threshold of magnitude u. And in this study, to identify the suitable threshold for each time scale, we are going to use the semi-parametric estimator, which is called as adapter Hill method. Okay, so this is some background of the Pickover threshold approach. Okay, where basically you select the values which exceed the threshold. Okay, which the selection of the threshold is based on 3 tests which satisfy the assumption of the extreme events. Basically is mean frequencies, mean occurrence, and threshold stability. Okay, and this is using the Pickover random threshold approach. Okay, for the semi-parametric approach, we work on the top k order statistic or with the excess over a high random threshold. Okay, so we choose the choice of the largest k order statistic in the sample is then based on the adaptive estimation of EV1, that is the shape parameter of GP distribution, and we select the optimum k, which is the k order statistic, or u, which is the threshold which is attained through the minimization of the asymptotic mean square error of the estimator. Okay, and this is the adapted Hill's estimator for the kth order statistic, and the minimization of the MSE of the parameter is performed via the semi-parametric bootstrap. Okay, so this is the procedure for the semi-parametric bootstrap algorithm, okay, as proposed by Kayes and Mice 1998, and this is our result. Okay, the table below gives the result of threshold selected. Okay, so this is for the 8th region. Okay, and this is for the 4 different time scales, and this is the threshold. Okay, and the threshold and the number of upper order statistic k, the mean frequency, okay, of accidents, and MSE. Okay, this is after several bootstrap to identify what is the most appropriate threshold for each region and for each time scale. Okay, so from here we can see that for the shorter duration, okay, the area region 6, which consists of area stations in Terengganu, okay, possess the lowest threshold. Okay, for duration 1 hour, okay, the region KL possess the lowest threshold value, and area 3 and area 4 for 24 hours. Okay, and in contrast, for the higher values of threshold U, you can see that the area Johor gives the highest threshold compared to other regions for the shorter duration rainfall. Okay, for 15 minutes, 1 hour, and 24 hours. Okay, the area of Johor and the east coast of Pahang. Okay, and for the longer one, 120 or 5 days rainfall is 214.7, which is given by the east coast or by Terengganu area, the Terengganu region. Okay, so based on the optimal threshold selected, we then derive all the data, okay, for each of the time scale. And the next one is on the fitting of the frequency distribution. Okay, we chose 4 frequency distribution, which is commonly applied in frequency distribution analysis, extreme frequency distribution analysis. Okay, and this is the goodness of fit that was used. Okay, the Z statistic, as well as we use the root mean square error. Okay, and this is all the statistics, okay, based on the fitting. Okay, and we found that based on the Z distribution goodness of fit, 40% of data favor the generalized normal distribution, while 52.5% data favor the GPA distribution, generalized Pareto. And also for the RMSE, the 87.5% data favor the generalized Pareto distribution. Okay, so not much which favor the logistic and the GEV. Okay, and application from this. Okay, so since we have fitted the data, okay, we are going to use the distribution, okay, to calculate some quantiles based on the distribution GPA. Okay, from GPA distribution for the 8 regions. Okay, from the 0.1, okay, 0.5 up until 0.9999. Okay, these are the quantiles values. Okay, and basically what it tells, by observing the higher non-accidents probability F, it can be found that the region 8 has the highest rainfall quantile for 0.25 hours. Okay, region 6. Okay, region 8 is, okay, so over here. So, okay, region 6 has the highest value for 124 and 120 hours, and region 7 has the lowest quantile. For 1 hour, region 5 has the lowest estimate, and 24 and 120 hour, region 3 gives the lowest estimate of the gives the lowest quantile estimate. And this showed that for long durations, region 3, okay, which is the west coast, has the lowest rainfall quantile, while region 6, which is located on the east coast, has the highest quantiles. So you can this actually match, of course, with this, okay, with this result over here that I have elaborated just now. Okay, so the next analysis is the trend analysis. Okay, over the past several decades, climate change has been consistently associated with changes in several components of hydrological cycle and systems, such as precipitation patterns, intensity, and extreme. Okay, and the impact of these changes can be detected with various statistical and stochastic techniques to identify the trends and shift in hydrological series at different temporal scales of aggregation. And in this study, we are going to use 2 rainfall indices, namely the extreme intensity of wet days and extreme frequency, okay, to analyze for the trends. And we are going to use the linear regression test and the man candle test. Okay, and this is the result for the extreme frequency and extreme intensity. Okay, so you can see here, okay, for extreme frequency, we can see there are some significant, okay, positive trend, okay, at the sub-regions, okay, particularly region 2, 3, and 4, okay. But for extreme intensity, okay, there's not much change, okay, and most of the slope is about 0, okay, which indicate there's no change in the extreme intensity, okay. For extreme frequency, region 4 has significant positive trends for all the 4 durations, 4 time scales. The largest positive trends for 0.25 and 1 hour duration are provided by region 6, and for 24 and 120 hour duration, regions 4 and 5 have the largest positive trend. And for extreme intensity, all estimates of slope parameter and S statistic for 15 minutes has negative value. This means the extreme rainfall for 0.25 hour durations has decreasing trend over the 40-year study period. Okay. However, for the 24-hour and 120-hour duration, the slope parameters for all regions are close to 0, implying that, okay, no change in trend. Okay. So in conclusion, okay, what this study we have managed to delineate, okay, 8 regions from 80. We have managed to delineate from 80 stations to become 8 regions. And the best fit frequency distribution for extreme data is the generalized Pareto distribution. Region 6 has the highest rainfall quantile for 1, 24 and 120 hour. And this means heavy rainfall is observed in this region. Okay. Meanwhile, region 3 is the lowest quantile estimate for 24 and 120 hour duration. Hence, it can be concluded for long durations, West Coast has heavier rainfall compared to East Coast. Based on the trend test result, it can be concluded that although the extreme intensity are decreasing for short duration and no significant change for long duration, the frequency are showing positive trends. Okay, so that's all I have, and I think I should have put inside all my slides. We got the conclusion this map, so you can see while I presented what are the specific regions where we got the result of the analysis. Okay, that's all I have. Any question?
Okay, any questions? Dr. Wan said she required a question. Yes, please.
Assalamualaikum. I have one question to ask. For cluster analysis, you have selected 7 attributes that you mentioned just now. So is this the important parameters that you need to consider in order to do the or to analyze the cluster, to get the cluster?
Okay, based on literature, when I look into the Watts method of regional frequency analysis, okay, for cluster analysis, it is suggested that there are several criteria that you can choose, okay, when you're doing clustering, okay. One could be the location, the specific location of where the data is taken, okay. So in this case, it will be the longitude, latitude. And the other factor, there are several other attributes. The other factor is the hydrometeorological variable, okay. So since we have the data on the total rainfall, okay, so I decided to use that data, okay, as well as the mean of the annual precipitation, okay, to form the cluster for the attributes.
And another one question. Why did you accumulate the total rainfall? So just because I've read somewhere else, because if you got 4 seasons, for example, so the accumulation rainfall is, for example, the autumn season,
yes,
summer.
We don't have obvious. Okay.
So why did you choose to accumulate the January, February, March instead of maybe you can consider monsoon rainfall in your calculation?
Yeah, that's a good question, which we actually we were trying to find the appropriate attributes, okay. So basically why we did this is, if you can observe, from April, May, June and July, September, August, September is considered as dry season. Okay, dry season, and October, November, December, January, February, March is a relatively wet season. Okay, but the total rainfall is different. Okay, compared to, if you to compare between the East Coast and the West Coast. Okay, so in this case, we think that it's better if you were to group it to 3 months difference. Okay, so because we will expect that in the October, November, December, the east area will experience higher total rainfall. Okay, and relative to the west part, as well as there are, from the total rainfall that we calculated, there are slight different when we look at the behavior in January, February and March. Okay, especially in February and March, it's more on the convective rainfall at the west area. Okay, and another attribute that we may consider, which, because we don't have information here, is also the altitude, okay, of the station, which, if you have the information, you can also add into the cluster analysis to improve the clustering.
Because I think it reflects your cluster analysis. You can see your next slide.
Okay.
Because you can see the region, it's not spatially distributed.
It's not spatially distributed. We have the north here, and the northwest are considered not really north. Okay, and this one, this is rather spatially distributed, I think. Apart from here, okay, this from here, which is the region 4 here, and this is the basically the highland of the Pahang, and we have the Johor, and as well as Pahang here, and Kelantan and Terengganu. Okay. No, it can be, I think it will be based on how you define your attributes. Okay.
I think the best cluster, 4 and I think 4 is
yes, because we want to, if possible, to delineate, to create as many regions as possible, but still acceptable for the analysis. Of course, usually, okay, I also did the logical clustering. Okay, basically I just divide by 4. Okay, because we know that over here is very heavy rainfall, similar characteristic, and over here, okay, also heavy rainfall, but maybe at different months. And this one, and also this is the relatively dry area. Okay, but we want to zoom into more details of the differences in the regions. So that's why we add, okay, specifics, these 4 attributes here, which somehow managed to delineate, okay, which managed to, we come out with the 8 regions here. Okay, but of course, if you choose different attributes, it may not give you the same result. Okay.
Okay, there is a question from me. Where's the best place to stay in Malaysia?
Where's the best place to stay?
To avoid the flood, because...
To avoid the flood?
Yes.
Okay, the answer is rather obvious. If you want to avoid the banjir kilat, you won't stay here. If you want to avoid the monsoon, monsoon Timur Laut, then you won't be staying here. This area is relatively dry. This area also at times got flooded. So where do you want to stay? You want to stay at Penang? It's a bit congested. Or you want to stay at Pahang?
It's good to have the flood occurrence and compare with the monthly.
Yes.
That's the best thing to do, because nowadays people think about where's the place that no flood but it's good to stay. Now, Kelantan is not nice to stay anymore. Big flood. Pahang also similar. In Klang Valley also not safe place. Kajang always flooding. In KL also. It's good to have the relationship between the flood and the monthly rains. Because sometimes it's flood occurs because of 1 or 2 day rains, not because of the monthly rains. Only 1 day or 2 days heavily rain is flooded.
Okay.
Yeah.
That will be the rainfall runoff analysis.
Yeah.
Okay. Inshallah, that will be the further the future analysis will be on the rainfall and runoff.
Okay. Anybody else want to ask questions? Okay. Thank you very much, Dr. Wan.